All right, good afternoon, everybody. Let's get started. Welcome to 644. Today we're going to continue our discussion on hardware support for operating systems. And in particular, we're going to focus on the remaining piece of the puzzle on how to implement virtual memory. So remember that operating systems seek to have these three different goals: protection, having a private address space for its different process that is sharing the machine, and that address space should be controlled by the operating system. Then abstraction, hiding all the details of the underlying hardware. So for example, processes manipulate files instead of writing to disk directly, right? Issuing raw commands to hard drives or to other devices. And then resource management, right? Seeing how much CPU, how much memory, how much disk space each application or each user gets. So in terms of hardware mechanisms, right? Last lecture, we focused on basically virtualizing the CPU. So we saw how in hardware we needed this combination of a user mode plus a supervisor mode that has some additional instructions and some additional state, some additional capabilities. And so the operating system will be in supervisor mode, all other processes run in user mode. And then we have these exceptions or interrupts, and this exception mechanism that lets us transition from a process into the operating system safely. Right, and we saw multiple use cases of exceptions. You know, we use them to schedule processes into the CPU, essentially dividing or time multiplexing the CPU among multiple processes. We use them to emulate instructions and so on. And so in recitation yesterday, you hopefully saw those in much more concrete detail with the demo of the RISC-V operating system. Now, the last piece of the puzzle is virtual memory. It's essentially the technology that we use to implement this protection mechanism, right? The fact that processes cannot access each other's memory. Instead, each of them has a private address space. And we also use this to abstract the storage resources of the machine. And this is what we'll focus on today. And so at a high level, we want virtual memory systems to provide two features. Essentially, the first one is this private address space that we've seen in some detail so far. So we're going to have some physical memory reserved for the operating system, and then its process is going to be in some part of physical memory, in some disjoint region of physical memory. But they're all going to believe that they have some amount of memory all for themselves. The other feature that we haven't seen so far, but it is also extremely useful, is what we call demand paging. And demand paging essentially stands for using main memory as a cache of disk. So, you know, a constant of the universe is that we always want to store more data than we have memory available. And so it doesn't matter whether your machines have 32 kilobytes of memory or 2 terabytes of memory like they do today. There's always some application that demands more memory. And so the same way that a week ago we started our discussion of the memory hierarchy, remember that we had hardware caches and a whole hierarchy of caches before main memory. Now we're going to see the other end of the hierarchy. So once you go past main memory and into disks, right, into flash drives or spinning drives, what is the mechanism that we use to transfer data between those, and how can we give the illusion that we have a very large main memory, even though we actually have a main memory that is limited by the amount of DRAM that we have, and then a much larger hard drive. So this has two advantages. Just like caches let you run programs that exceed the size of the cache, this lets you run programs that exceed the size of main memory. And also, this will hide the differences in machine configuration. What I mean by that is that every process written for the same ISA will see virtual addresses, or will see an address space of the same size. Even if you have a machine with 1 gigabyte or 2 gigabytes of memory and then decide to add some main memory, right? So essentially it's hiding the implementation or the particular amount of main memory that the system has. Now these abilities or these benefits come with a price. And so the price is that now, for every address that our process produces, for every memory access, either an instruction access or a data access, that our process wants to make, we need to translate the address, that address, into a physical address. And that is going to require some hardware, and we'll see how to make that fast. And so in terms of computer architecture innovations, we will, we've already seen things like caches. Next week we'll focus on pipelining, and all of those things, are very effective techniques to make computers faster. Virtual memory is not like that, right? Virtual memory is adding a heavy price, and then we're adding a lot of hardware to actually make that overhead smaller, but it is not making anything faster. And yet, if you ask computer architects or computer system designers, they will tell you that this is perhaps the most important innovation in computer architecture. So these techniques were designed in the 50s, in the 60s, and even though they're pretty old, they're still in use today, and there's still significant hardware going into systems, into making virtual memory fast. And that is because virtual memory is crucial to make systems reliable, to make systems work, right? So it doesn't matter if the system is very fast if one program can corrupt the state of the whole machine or can take over the machine. Okay, so at a high level, let's start with a little bit of nomenclature. On the one hand, we have a process, right? And the process is generating addresses for both loads and stores and also instruction fetches. And we're going to call these virtual addresses, right? Because these addresses are specific to the process, to the process's private address space. And what we're going to do is have some address mapping function. We're going to have some scheme that is under the control of the operating system to translate these virtual addresses into physical addresses. Now we're going to access memory using these physical addresses. And we call this memory physical memory, right? Hardware memory. That's what I mean by physical. And the key the key thing to remember here is that this address mapping is under the control of the operating system. Right? That is why we're going to be able to have protection among different processes. Okay. So there are two techniques that we're going to see, segmentation and paging. Segmentation is the simplest technique, so we'll start with that one. So essentially segmentation, which sometimes is called base and bound address translation, works as follows. You have the address space of each process, and the address space starts at address 0 and goes up to some address. In this case, is hex FFF. So there's 12 bits of address space. There's basically 4 kilobytes. But in physical memory, that address 0 does not map to physical address 0. Instead, what we're going to do is allocate a contiguous segment, right, just a contiguous chunk of physical memory to store the whole address space. So in this case, this is 4 kilobytes of address space. We're going to allocate 4 kilobytes somewhere in physical memory to hold all the data of this process, both the code and the data. Then what we'll do is we'll have a base register that points to the first address of this segment, to the starting address of this segment. And every time the process issues a memory reference, right, every time it does a load or a store or fetches an instruction, we will translate from the virtual address to the physical address by adding the base register. Right, so for example, if this is hex 4000, right, then we will add 4000 to whatever address, to whatever virtual address to produce the physical address here. Right, so essentially we're just adding a constant value, or adding the contents of the base register to produce the physical address. So this translation is very easy, and so that's a great benefit of segmentation. And then the other thing that we want, remember, is to avoid or to prevent this process from accessing the data of some other process that might be sharing the machine. So this picture is showing the memory allocation for a single process. But somewhere below here, there might be data for some other process, right? And so we also want to prevent any out-of-bounds accesses, right? Any access to an address that's larger than this largest address that we have allocated to the process. And to do that, we add a bound register. And so for every virtual address that we want to translate in parallel, we also compare it with the contents of the bound register. And the bound register in this case would be hex FFF, right? If it's within the bounds, right, then the access proceeds. But if the process tries to access a very large address, something that is, in virtual address, in its own virtual address space, it would be here, right? And this would map to somewhere here in physical memory, so out of bounds. Then the process, or the processor, the CPU, will raise an exception, which we call a bound violation exception, right? Because the process is trying to do something that it shouldn't. It's trying to issue a memory access to an address it doesn't have permission to access. Okay, so that way we can isolate multiple processes, right? And of course, a detail here is that these two registers must be privileged state, because we do not want the process itself to be able to access and modify its own base and bound registers, right? Otherwise, the process could itself give itself access to all of physical memory, right? So again, we're going to rely on exceptions. We're going to rely on privileged state to avoid or to prevent the user processes from accessing or changing things that they should not. Okay, any questions? All right, so let's see, one simple variant of this segmentation technique. So here, I've shown a single segment for the whole program. But there are some benefits to having at least two segments. And so here, I'm showing two different segments, one for data and one for code. So here, what we're going to do is all the loads and stores are going to go through the data segment. So we're going to have two pairs of registers, the database register and the data bound register, and then the code-based registers and the code bound register. We're going to take all load and store addresses and pass them, or do translation using these registers, just like we saw before. And then we're going to take all the instruction fetches, that is the values of the program counter, and then do address translation using the code segment data, right? The code segment registers. So what are some benefits of having this separation? Why is it good to separate data and code? You might have stumbled upon this in lab 2 or in lab 1, where you were writing assembly, and if you messed up the address of a store, it was possible to go ahead and overwrite the code, which would lead to all sorts of weird behavior, because now the instruction that should be there is not there. There's some garbage data, and so the processor will start misbehaving because you've overwritten some of your code, right? So can this happen with this mechanism? Can I have a store that overwrites my code? I see many of you shaking your head. Exactly, right? You can't, because all these accesses are checked, right? And they go to separate pieces of physical memory, right? So, we're talking about isolation among processes, and the previous technique, if you have a single segment, you can isolate different processes from each other. But if you have these two segments, you can actually isolate a process from itself, which is good because it will reduce the damage of bugs, right? Okay, another benefit that's less obvious is that it's often the case that you'll have multiple programs that are running the same code or are sharing, a large part of the code. And so what this also allows the machine to do is to have the same code segment for all the programs in the machine or for a subset of the programs in the machine, and then have separate data segments. So it's also going to allow the system to make more efficient use of resources, because instead of having a separate copy of the code for each program, we can now have all programs or many programs share the same code segment, right? So because of this technique is actually used in a few types of systems. So if you use a GPU, you'll likely run into segmentation done in this fashion. And some other specialized or low-power processors also tend to use this mechanism. But in fact, segmentation is very rarely used in general-purpose processors today. So the processor that you have in your cell phone or in your laptop, they're using something a little bit more sophisticated. And the reason is that there's one key problem with segmentation, and that is called memory fragmentation. Essentially what happens is that as processes are created and they change their memory allocations and they finish, physical memory becomes fragmented. Let's see this with a concrete example. So this picture here shows 3 different processes, process 1, 2, and 3, that have different separate segments allocated in different regions of physical memory, right? So we have some space allocated to the operating system, and then process 1 has some 16 kilobyte segment, process 2 has a 24 kilobyte segment, and process 3 has a 32 kilobyte segment. And between these, there are 2 24 kilobyte segments, or 2 24 kilobyte chunks of free space that we can use for other processes. Now let's say that we have 2 other processes start, so we give them 16 kilobytes to process 4 and 24 kilobytes to process 5, and now we only have 8 kilobytes of free space over here. And now if, let's say, processes 2 and process 5 end, now we have this chunk of 24 kilobytes of free space, 8 kilobytes of free space over here, and 24 kilobytes of free space. And we've gone from having 2 free chunks to 3 separate free chunks. And even though we have more space, there's still no way to start, for example, a process that requires 32 kilobytes of space. Right? So now we have these separate little chunks of free space. And if you wanted to start a process that required 32 kilobytes, I mean, you could do it, right? We could do something like move process 4 down 8 kilobytes, or move process 4 over here, which would give us a 48 kilobyte segment. But we're talking about moving a large amount of memory, right, every time that we need some extra memory, which is expensive. And you might not think this is expensive because then these numbers are pretty small. What is 16 kilobytes of data these days? But if we were actually giving gigabytes of data in a single segment, then you can imagine that moving 1 or 2 gigabytes of data up and down memory would be very, very expensive, right? So we don't want to be moving data up and down memory just to make space, right, for processes that want more data. And even worse, you also want processes to allocate and to release memory as they need more or less, right? So a process might go through multiple phases. Maybe it needs to read some large input, right? And so it allocates a lot of memory to hold that input first. But then it does some processing that requires a small amount of memory, and it releases most of the memory that it allocated, right? It would be great if the operating system could reuse that physical memory for something else, like some other process, right? So that is hard to do with segmentation. So the takeaway here is that segmentation is very, very simple, right? But it's kind of inflexible. Having all the memory or all the address space or the whole address space of each process as a single contiguous chunk of physical memory is problematic when we want to manage the physical memory for several processes, right? When we want to dynamically allocate or release memory. So the solution to this is what we call paging. So paging is a technique where instead of storing each segment as a single contiguous chunk of physical memory, we first divide physical memory in small fixed size blocks, and we call those blocks pages. You can think of these as cache lines. Just like we divide main memory in cache lines, there's some other fixed size block that then we're going to manage main memory in. We call this, again, a memory page. So, the particular size of the page will depend on the system, but typically we have 4 kilobytes, 8 kilobytes is a typical size for a page. And then what we do is we allow each process to have its virtual address space consist of some disjoint set of pages. And to do this, we have to do a level of address translation that's a little bit more sophisticated. What we're going to do is have this extra structure, this new structure that we call a page table. Right? So first, we're going to divide each virtual address into 2 components. The offset, which is log2 of the size of the page. So for example, with 4 kilobyte pages and byte addresses, we would have 12 bits of offset. And then the rest is the virtual page number, which is essentially telling us, the part of the address that tells us which page in the virtual address space is this address referring to. And then we're going to go through an auxiliary structure that we call the page table that holds the mappings of each virtual page number to each physical page number. So it tells us for this particular page number over here, what location in physical memory, what page in physical memory does this virtual page map to. Okay, let's see this pictorially in a little bit more detail because this diagram is kind of abstract. So this diagram shows 3 different processes with each of them with their own virtual address spaces and each of them with its own page table. So the page table is going to be a structure that is going to be private to each process. And then on the right here we have physical memory. So again we have some space reserved for the operating system. And then we have pages of the different processes in the remainder of the physical memory. And let's just see how one of these addresses is translated for all different processes. So let's say that process 1 has a virtual address space that consists of 3 pages. Each of these cells here, each of these blocks, denotes a page. And let's say that you have, virtual address 1. So you have a virtual address, and we're going to interpret this as 2 things. The virtual page number and the offset. This virtual page number for VA1, if you just count, this is page 0, this is page 1, right? So this VPN, in our particular case, is 1. So what we'll do is go to the first, or to entry number 1 of the page table, and this will give us the physical page number. That is the page, the index of the page in physical memory that holds the contents of this virtual page. So you can see that each of these page tables has pointers, right, to different locations in physical memory. So in this particular case, right, essentially this entry is pointing here. And you can see that this is this location over here for process 1. Right? Now for process 2 also has page 1, which holds virtual address 1. And so we would go to make this translation to the page table of process 2, and then look at here. So we have this pointer over here. So this is the physical page associated with the virtual page of process 2, virtual page 1, process 2. So you can see that the first virtual address maps to different physical addresses in different processes, achieving essentially what we want, having this private address space. But then there's also this important detail that, as you can see here, different processes have their address space stored non-contiguously. Right? So for example, process 2 has one page over here and a couple of pages over here. They're not stored contiguously in main memory anymore, just like they were with segmentation. Right? Instead, they're mapped to different physical pages that can be all over the place in physical memory. Right? And by having this, we have a much more flexible mapping that is much easier to manage. Right? So in summary, paging is going to give us one main, or one benefit that we've already seen of paging versus segmentation, is that we avoid the fragmentation problem, because now we can just manage these fixed size pages instead of variable size chunks of free space. And as long as we have sufficient memory, we do not need to move anything. Right? As long as we have a free page, we can give it to a process that needs it. The second good thing is that it allows us to do demand pages. And this is the first thing that we'll see in the remainder of this lecture. It's going to allow us to essentially use main memory as a cache of disk. So without getting into the details of why this happens, we'll see this in a couple of slides when we look at the specific format of the page table. There's, before we do that, I want to sort of focus on what we're giving up here, right? Because we went from just having a couple of registers to a page table. And what's the problem there? Why is that bad? So you have a more flexible mapping, but how much space is it going to take me to store the page table versus the information that I need to locate a single segment in physical memory? So we're going from 2 registers to something like kilobytes or megabytes, right, worth of translations, of mappings from virtual page number to physical page number. So this flexibility comes at a cost. And so, of course, the immediate question is, okay, with segmentation it was obvious that we could store this in registers, right? It's just 2 numbers. But where do we store the page tables? Any guesses? So they take a lot of space. We might as well store them in main memory. Right? So the page tables themselves are in main memory. So here's how it works. For each access, let's say we have a process in process 1 in the schedule in the CPU, we have a privileged page table based register that is going to tell us the starting address of the page table in physical memory. We're going to take the virtual page number, right, and use it to index into the page table to find the physical page number associated with this reference. And then we're going to go to the particular page here and get the data. Right? So, in other words, the translation is now 2 memory accesses. First, 1 memory access to find the physical page number and find the physical address. And then the access to actually get the data. Right? So accessing 1 thing from memory now requires 2 memory accesses. The other problem, I mean, the other side of this picture is where do you store the information about the page tables themselves? And that's somewhere in the kernel page table. And so what happens is, when you context switch, the kernel will change the contents of this page table base register. So for example, if we put if we switch in process 2, then this base register will point here, right? So that we can switch the page table. But the key thing that I want to highlight here is that we've gone from 1 memory access to 2 memory accesses, which is problematic, right? Because memory accesses are expensive. And by the way, I want you to, for a second, forget that we have caches. We'll talk about the interactions of caches with virtual memory in the last couple of slides. But for now, let's just think that we have a CPU, then main memory, then a hard drive, right? And that we don't have any data caches. Okay, so in the rest of the lecture, what we're going to do is first see how demand paging works, right? See the benefit that we get from paging, the second big benefit that we get from paging. And then we'll see how to solve this problem. Okay, so demand paging, as I mentioned, the key idea is to use main memory as a cache for disk. So we're going to have a large hard drive that's going to have much more capacity than our main memory. And so then what we want, this is going to determine what our page table holds, right? And so specifically now we have enough information to go and figure out what pieces of data we need in each page table entry, right? In each location of the page table, so that we can make a translation from virtual page number to physical page number. So the page table is going to look like this, right? This is a linear array of pages that we're going to index with the virtual page number. And then we're going to, essentially at each entry, we will have 3 different types of information. The first thing is our resident bit. We're going to have a special bit that tells us whether the page is in main memory or it's on disk. If the page is in main memory, which that's when we say it's resident, then we're going to have a physical page number for the page, right? So for example, this entry over here, this is a resident entry. This virtual page is somewhere in main memory. So it is. So we get the physical page number, and then we can figure out what the physical address is by adding the page offset into it, right? And that way we get the physical address for the word that we want. On the other hand, there are pages that are not resident, that we do not have in main memory, and instead are on disk. And in that case, if the resident bit is 0, then the page table for that entry holds what we call the disk page number, or DPN. That's just some information so that we can go and locate the page from disk and bring it from disk. Then there's going to be also some protection and usage bits. So things like, is this page writable? Can I write to it? Right? For example, if you have a page full of code, maybe it's a bad idea to allow the process to write to it. Or if it is writable, is it dirty or is it clean? Right? So that when the operating system needs to evict this page to disk, it knows to write it back instead of dropping it and not writing it back. And then what this enables is that even if all pages fit in main memory, so even for situations where the operating system and the machine has sufficient memory, it lets the operating system be lazy. Right? So when you start a program, imagine that you have some giant program that takes hundreds of megabytes of code. So the operating system could bring those hundreds of megabytes into main memory, or it could just bring the first page of code and start running that. And when the process tries to jump somewhere else, then the operating system will bring the page that it wants, that the process wants. Right? That is good because, for example, think about the case where you have a program that is 100 megabytes of code, but it throws an error or it does something very simple and then it just exits. Right? That way you don't need to bring all the data. You can just the operating system can be lazy. Okay, so let's see this with a much more concrete example. So here we have, the following setup. We have a machine that has 256 bytes per page, so that's 2 to the 8 bytes per page, and therefore we will have 8 offset bits, right? And then we have 16 virtual pages and 8 physical pages in our system. Generally, the system does not need to have the same number of virtual and physical pages. Some systems have fewer physical pages than virtual pages. That's sort of the general approach. So virtual memory is cheap to make reasonably large. And so, for example, in your machines today, you have systems that have 48 bits of physical addresses, but probably will have somewhere around 36 or 40 bits of physical addresses. But sometimes you actually have more physical pages than virtual pages, and you'll see problems of both styles in recitation. So what this means is that if we have 16 virtual pages and 8 bits per page offset, then we have 12-bit virtual addresses and 11-bit virtual addresses, right? So now the question is, suppose that I have this instruction over here where I'm accessing virtual address hex 2C8, right? So I have so the first thing is, from this virtual address, what is the offset and what is the physical page number? What is the offset and what is the virtual page number? Well, so this 256 bytes per page is chosen basically so that we can do this problem in hex, because that's just 8 bits. And so this is the offset, right? And this is the VPN. So now that we have the virtual page number, what do? We go to the page table. So our page table is going to have 16 entries, and we need to go to entry 2, right? So before that, let me just spend a second telling you about the precise format of this page table. So each page table entry is going to have 3 bits apart from the physical page number. The first one is the D, or dirty bit. Then the W, or writable bit, tells us where we can issue stores to this. And then finally the R, or resident bit. So here, if we go and look into entry 2, we see that the resident bit is 1. And so that means that this page is resident. And we get from the page table that the physical page number is 4, right? So now our physical address is 0x4, the physical page number, concatenated with the offset, right? Okay, any questions? Good. So the other question is, we've seen what happens on a hit, right? We've seen what happens when the page is already in main memory. But what happens on a miss? Well, on a miss, essentially we need to implement a cache, and we have exactly the same trade-offs, right? Exactly the same design decisions that we had with normal hardware caches. However, the key thing to remember here is that the difference between caching and demand paging is that all the design decisions in demand paging are driven by the huge cost of each miss, right? So a miss from a hardware cache into main memory is going to take about 100 cycles in modern technology, which may sound like a lot, but it's not actually that much. At least in comparison to what happens if you have to fetch the page from disk when you spend about 10 milliseconds or 5 million cycles. So 5 million cycles, if each miss is 5 million cycles, you're going to design your cache to minimize misses above all else, right? So we're going to have large blocks. This is why we have 4 kilobytes or larger pages. This is why the design of this page table is essentially, you can think of this as a fully associative cache. Why is it a fully associative cache? Because each virtual page can be mapped to any physical page in the address space, right? We don't have any addressing restrictions, because if we can avoid conflict misses, then things will be much easier for us. And the saving grace here is that since misses are so incredibly expensive, since getting something from this implies that we need to pause the process and run something else, because this is going to take essentially infinite time from the perspective of the processor, we can handle the miss in software, right? So whereas with caches, we need logic to handle misses, in demand paging, we're going to do everything in software. And so this is done by any time that a CPU accesses a page and finds the resident bit set to 0, it just triggers a fault. And we call this, or an exception, and we call this exception a page fault. A page fault is essentially telling the OS, hey, the page is not here, do something about it, right? So then the operating system will step in, right? The operating system exception handler will step in and say, okay, this translation, this page is not here, it's actually on disk. Right? It will see that this has a disk page number, it will figure out where it is on disk. And then it needs to do the usual things that we do to handle a miss. Right? It will find some other page in physical memory, in this case, let's say this one, that it will choose as the victim. It will choose its space to evict, to hold the page that we're going to bring from disk, and then it will first evict this page, write this page out somewhere on disk, and mark this page as not resident. And it will also bring in this page, right, from disk into main memory and mark it as resident in the page table, right? So it is at the end, after the operating system handles the page fault, we have this situation where virtual page number 1 is on disk, and virtual page 5 is now where virtual page 1 was. So the only thing that we need to do now is to just return control to the process and return control at the same address that issued or that suffered the page fault. And then the process will keep going, right? Because now VPN 5 is resident. So we won't trigger the page fault. All right. Any questions? Okay, so again, because misses are so expensive, we do them in software. That's nice. That's less hardware that we need to implement. The problem is we still have this issue that we need to access the 2 memory accesses for each reference, right? Because we need to access the page table to figure out the physical address. So what's the solution here? We've already seen this approach. We add a cache. And instead of a cache for data, it's a cache for address translations. And we call this cache a translation look-aside buffer. You could call it a translation cache, but that's the standard name, a TLB. So this picture shows the structure of a TLB. It is just like a normal cache, like the caches we've already seen. You have a tag, and the tag in this case is the virtual page number, right? So on every memory access, we take the virtual page number and we index into the TLB. We figure out whether the TLB already has the translation that we want. And the translation will be, both the physical page number, but also the other bits of the page table entry, right? The resident bit, the writable bit, the dirty bit, and then we also have a valid bit to figure out, where this entry is actually valid, just like we did in a cache, right? If there's a tag match, and these bits match with the access that we want to do, right? The page is resident, we're not doing a write to a page that's read-only, then we have a hit, and we just take the physical page number from here and perform the access as usual in a single cycle, right? Now we have a very small structure that's very cheap, and we'll do the access very quickly. But on a TLB miss, that is if there's no match here, then we need to access the page table, and only then we go and do a memory access to refill the data from the TLB. Okay, so you have this example here, which I am going to skip in the interest of time. You should go through this. This essentially asks you to first figure out how, what the size of the different structures in main memory is and what the size of the page table is. And let me just go through one particular translation here, just as a quick example. So let's start with the question 6 here, which is what is the physical address for virtual address hex 1084? Right, and so in this case, no. Okay. So 1804. Now in this case, our page size is 2 to the 10 bytes. And so we actually do need to translate this to binary. So 1804. And these 10 bits are our offset. This is our virtual page number, which back to hex, this is 6, right? So what do? We go and access the TLB, right? We see, is there a tag 6? Yes. Is that valid? Yes. Is that resident? Yes. What is the physical page number corresponding to it? 2. Okay? So from the TLB, we're getting that the physical page number is 2. So our physical address is just flipping this bit from 1 to 0. That is 0x804, right? And so the other axes here are illustrating what happens when you have a TLB miss and a page fault. Okay, so we have different choices in how to design the TLB. TLBs, just like caches, are typically set associative. They're generally small because we want to access them in a single cycle. So you'll see that generally they have a few tens to hundreds of entries. And just like we play this trick with caches where we have multiple cache levels when memory latency is very high, we also have, in modern processors, you'll see that there's typically a level 1 TLB and then a larger level 2 TLB. And only after you miss in the L2 TLB does the processor go to memory. Now, this TLB holds translations that are specific to the process it's currently running. So every time there's a context switch, every time we go from, let's say process 1 to the operating system or the operating system to process 2, we have to flush it, right? Which is expensive, especially if we have a large TLB. And so what happens is if the TLB is large, typically what will happen is that the process ID will be also part of the tag. So that way we don't have to flush the entire TLB on its context switch. So that is a design alternative, right? We can add the process ID to the tag, and that will make tag matches more expensive, but we avoid flashes. And finally, on a TLB miss, we need to go to the page table, and if the page is in memory, then we update the TLB, otherwise we trigger a page fault. Let's see how this happens in a more visual representation. So each memory reference begins with a TLB lookup. If you have a hit, right, if you have a matching virtual page number, then we issue a protection check, right? We look at the valid, or we look at the resident and writable bits. If the bits don't match what we want to do, right, if the page is not writable, for example, we issue a protection fault and take an exception and go to the operating system. Otherwise, if things match, we just return the physical address and let the CPU go to memory with that address. Now the interesting case is, what if the address is not in the TLB, right? Then we go and do a lookup on the page table, just issue a memory access to see where what the page table entry is, and use those contents to update the TLB. Now, this can either be done in hardware or software. Most of the modern architectures we use today, they do this in hardware. And so this diagram shows what happens in hardware. But you could do it, by throwing an exception on every miss and then letting the operating system fill the TLB through, let's say, special instructions, right? Privileged instructions. But assuming that everything happens in hardware, if you find a resident page table, we just update the TLB and go back to the protection check, just like we saw before. Otherwise, if the page is not resident, then we trigger a page fault. And then the operating system will handle the right translation and will resume the process at the instruction that caused the fault. Okay, so the last thing that we need to deal with is actually a important detail, which is that so far we've assumed that we have no caches. But in real systems, we have both caches, data caches, and we also have the TLB. And so the question is, where do we put the TLB? Do we put it in front of the cache or behind the cache? One option is to have the cache hold virtual addresses. This is what we call a virtually addressed cache. And so it's only after a cache miss that we go to the TLB. This is great because most of the time, we'll be getting cache hits and we won't be even touching the TLB. We won't even need to do translations. But the problem here, just like we needed to flush the TLB, is that we need to flush the cache every time we have a context switch. And this is very expensive. If flashing the TLB was kind of expensive, this is really, we want to avoid this. So the alternative is to do what we call a physically addressed cache. So in a physically addressed cache, we put the TLB before the cache, and then this cache holds physical addresses. The problem here is that to every memory access, we're now adding the latency of a TLB access. And so now this needs to happen sequentially. So there is a design trick by which we can adopt a design that's very similar to this, but do these lookups in parallel. And let me just tell you what that is. Now, when you're looking at pages, right, you have the page offset and you have the virtual page number. And when you're looking at caches, you have the offset bits for the line and the index bits. If your cache is small enough that the index falls within the page offset, as shown here, then you can actually start the lookup of the cache and the lookup to the TLB in parallel. Why? Because the lookup of the TLB depends only on the virtual page number, and the lookup to the cache depends only on the index bits. And if the index bits are within the page offset bits, then we can start the lookup here. This is a trick that pretty much all modern computers use. And the only issue is that, of course, we need to ensure that our index bits fall within the offset. So it's going to limit the size of our cache eventually. But at least for level 1 caches, this trick is used all over the place. Okay, so that's it for today. Next lecture, we'll start looking at pipeline processors. Thank you.